Good evening, folks, and welcome to the Advent of Code C++ live stream. It is just a couple of minutes until the puzzles for Day 8 drop. Thank you all for joining me tonight. If you're watching the live stream on Twitch or you're watching the replay later on YouTube, for all the puzzles that we work on tonight, all the code that we're going to write is going to go up in my GitHub repository. You can find the link to that either in my channel description if you're watching on Twitch, or right down in the video description if you're watching on YouTube. So, we are just about ready to get started on Day 8's puzzles. As always, I have a little skeleton of a program here. I need to put in, actually, its proper dependencies, because I already included my check library and my IO library, because we seem to use those pretty much every day. So we might as well get a little bit of a head start with those. And let's go ahead and just make sure that this little executable runs okay. So let's say run config equals LLVM. That's the LLVM toolchain configuration that I have set up, just because I like to use the LLVM tools instead of GCC. And we'll do an optimized build, and we'll just give it the path to the target, which is puzzles/day8 part 1. Go ahead and run that. Okay, we are good to go. So that debug information there is just about this new thing that I'm trying to get set up. Don't have it working quite yet, but that will hopefully make the tooling with ClangD a little bit better so it can find includes easier. But for now, I don't have that working, so we'll just use the ClangD setup that we've had so far. We have just about 30 seconds until tonight's puzzle unlocks. You can see more and more of this picture forming, this ASCII art that we unlock a little bit more of each day as we delve deeper and deeper into the ocean in our search for the lost sleigh keys. Okay. 7-segment search. You barely reach the safety of the cave when the whale smashes into the cave mouth, collapsing it. Sensors indicate another exit at a much greater depth, so you have no choice but to press on. As your submarine slowly makes your way through the system, you notice that the 4-digit 7-segment displays in your submarine are malfunctioning. They must have been damaged. You'd be in trouble without them, so you better figure out what's wrong. Each digit of a 7-segment display is rendered by turning on or off any of 7 segments named A through G. So, yeah, it looks like it's illustrating the digits 0 through 9 and the segments A through G that make them up here. So to render a 1, only segment C and F would be turned on, etc. The problem is that the signals which control the segments have been mixed up on each display. Summary is still trying to display numbers by producing output on signal wires A through G, but those wires are connected to segments randomly. Worse, the wire segment connections are mixed up separately for each 4-digit display. The digits within a display use the same connections, though. So you might know that only signal wires B and G are turned on, but that doesn't mean that segments B and G are turned on. The only digit that uses 2 segments is 1, so that must mean that C and F are meant to be on. With that information, you still can't tell which wire goes to which segment. For that, you need to collect more information. Okay. Interesting. For each display, you watch the changing signals for a while and make a note of all 10 unique signal patterns you see, then write down a single 4-digit output value, your puzzle input. Using the signal patterns, you should be able to work out which pattern corresponds to which digit. For example, here's what you might see in a single entry in your notes. Your notes will all be on a single file. Each entry consists of 10 unique signal patterns, a vertical bar delimiter, and finally the 4-digit output value. Within an entry, the same wire segment connections are used, but you don't know what the connections actually are. The unique signal patterns correspond to the 10 different ways the submarine tries to render a digit using the current wire connections. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Because 7 is the only digit that uses 3 segments, dab in the above example means that to render 7, signal lines D, A, and B are on. Because 4 is the only digit that uses 4 segments. Okay. Using this information, you should be able to work out which combination of signal wires corresponds to each of the 10 digits. Then you can decode the 4-digit output value. Fortunately, in the above example, all of the digits in the output value use 5 segments and are therefore more difficult to deduce. For now, focus on the easy digits. So we've got a larger example here. Because the digits 1, 4, 7, and 8 each use a unique number of segments. You should be able to tell which combinations of signals correspond to those digits. Counting only digits in the output values, the part after the vertical bar on each line in the above example, there are 26 instances of digits that use a unique number of segments. Okay, the output value is how many times the digits 1, 4, 7, or 8 appear. So the let's go ahead and save that puzzle input, day08.txt, and let's give that a look. Okay. So each line is a different puzzle, and let's see. So the first part of this is actually pretty easy. I have a feeling in the second part we're actually going to have to figure out the decoding. But for now, let's just say, let's go ahead. And we will make a we'll make a representation of display here. So say say class display, and it's going to have inputs and outputs. So there are 10 unique signal patterns. Are the signal patterns... Oh, we only list they're not guaranteed to appear in any order, but they are unique. So we'll just go ahead and say, well, actually, before we write the display class, I'm going to have a class that called signal. And this is going to be really simple. It uses the segment display, and its actual representation is going to be just a bit field where A is the 0th bit, B is the 1th bit, C is the 2nd bit, etc. So to parse that, we just go through the string representation, and then for each character in that string representation, we'll say is go for C minus the ASCII value A, so that A will be 0, B will be 1, C will be 2, etc. We can go ahead and check that C is greater than or equal to 0, and also check that offset is greater than or equal to 0, and also that offset is less than 7. make sure everything's in range, and then we will say segments. We are going to OR in 1 left shifted by that offset. So that is our representation of a signal. And then for display, we're going to have, might as well, for now we're going to use array, I think. Because there's always going to be 10 inputs and, 10 distinct patterns that we count, and then 4 outputs on the right side. So we'll say, and we'll also go ahead and say, well, I'm going to add a method to this signal class that just counts the number of active segments. So we'll just say return. I think in C++20 there's actually a population count function, so I don't need to use the built-in. Yep. There is. So, and we are working in C++20, so we'll include this new bit header, and we'll say standard pop count of the segments. Okay. And then for display, we will once again write a constructor that parses it. So let's see here. I don't know why this would be a problem. Call it implicitly. Oh, okay. We're going to give signal a default constructor that just does nothing, that leaves everything empty, just so that these arrays can be initialized before we try and access them in the constructor of display. But yeah, we're going to go ahead and get a vector of string views, which are going to be the parts of that representation. We're going to use absol split to split those apart. So we'll go ahead and include the header for stir split. So we're going to split up that line representation. And we're just going to split stuff by just by the space character. So the first 10 elements are going to be the 10 different signal patterns. The 11th element is going to just be the vertical bar, and then the last 4 elements are going to be the output patterns. So there should be exactly 15 parts. So we will go ahead and check that, and then we will say for int pattern index equals 0. Up through 10. We will say that the element of all patterns at that index is equal to signal parsed from parts at that index. we'll go ahead and check that pattern index, parts at part 10 is equal to a string with just that vertical bar divider. And then we will fill in the outputs as well. So go through output index equals 0 out through 4. And we will say the output at that index is equal to signal parsed from parts at 11 plus that index. Okay. So, and then from display, the one more thing that we're going to need is to be able to count up the number of the digits with unique number of segments. So those are 1, 4, 7, and 8, and the actual number of segments that they use are 2, 4, 3, and 7, respectively. So we'll write a method called unique digits in output, which will just go for each signal in outputs. I will say int count equals 4. Say we'll just do a switch on signal on that signal dot active segments. And if the number of active segments is 2 for the digit 1, 3 for the digit 7, 4 for the digit 4, or 7 for the digit 8, then we will increase the count. Otherwise, default case, we will do nothing. And we will return that count. So now we just do the I/O part. So we'll say we have a vector of strings to represent the input, and we'll use one of our pre-written I/O routines, read lines from file, to read that from the file, which we specify as the first argument. And then we will make up a vector of displays. And each line we will parse as a display. So you go through each line, and then we will do emplace back on the vector of displays, passing that line. It gets forwarded to the constructor for display to construct that new display. And then we will count up the total unique digits, starting at 0 and then going through each display. In that vector of displays, and adding the unique digits in the output for that display to the total. And then finally, we will print that out. Okay. just need to include string there. We are using the absol string library in this, so we need to pull in that dependency as well, put that in our build file so that Basil knows that it needs it to build this part 1 solution. So I think we have everything that we need here. So I'm going to go ahead and run this with the day 8 input there and see what happens. Okay, it's saying 554 is the number of unique digits in our puzzle. Let's see if we are correct. All right, we got it. That's part 1. On to part 2. Through a little deduction, you should now be able to determine the remaining digits. Consider again the first example above. After some careful analysis, the mapping between signal and wires only makes sense in the following configuration. Okay? So unique signal patterns will correspond to the following digits. Then the 4 digits of the output value can be decoded. Therefore, okay, following the same process for each entry in the second larger example above, okay. So now we have to do our actual deduction. Each entry, determine all the wire segment connections and decode the 4-digit output values. What do you get if you add up all of the output values? Okay. Okay, now we have to actually solve the puzzle for reals. So first thing I'm going to do is make a little commit just with these changes to, just with the part 1 solution. And I'm going to go ahead and copy our source code for part 1. To form the basis for part 2. And I'll go ahead and add the part 2 target just by copying and pasting from part 1 in our build file. Okay, part 2. So, so let's think about the process of deduction here. We can know for sure what corresponds to 1, 4, 7, or 8. Just based on the number of bits that are set. So actually, like if we start counting this up, we can also see that like we know what the So I'm looking at the patterns here, and actually I'll go ahead and show that here. So for instance, for number 1. We will always know which one represents 1, and we'll know which one represents 7 just by the number of activated bits or activated segments. And we'll also know that the top elements here in 7 must be the only bit that's not set in 1. So you can probably get somewhere with that. Also going to look at the process of deduction here. Just looking at these patterns. So I'm also looking at, say, like 7 and well, okay. So if we look at 7 and 4, if we combine all the signals from those two together, then we'll get everything that's in 9 minus the bottom part, so that can give us the bottom part. So yeah. So now I'm thinking about how I want to represent this in the program. Yeah, we've got our first really tricky puzzle tonight. Let's see. So first thing I'm going to do is make signal. So I'm going to add some useful operators to signal. So for one, we'll be able to just check equality of one signal with another. Just by comparing their segments. And we can also hash it. So we can use it in like a lookup map here. Hash value. That should be type name, not template. There we go. Type name. Oh, it should be signal, not segment. Man, just messing up everywhere. I'm not sure if we'll actually use that in a hash-based container, but it's good to have just in case. So yeah, I'm just looking at these patterns, trying to figure out how I want to approach this. I mean, I guess it could probably be brute force too. I kind of want to try and be clever, but if we get 4 out of the way, then for each given pattern, there's, 6 remaining, and so not that many possible combinations to try, I guess. Hmm. just kind of staring at these segments here. Okay. Well, we're going to want, you know, a solve method here, essentially. And we'll save some signals here. We know that which ones represent 1, 4, 7, and 8. So let's just first go through all the patterns. Go ahead and switch signal dot active segments. Again, on that, sorry, that should be pattern now. And if it has 2 active, then we will assign that to sig1 and break. If it has 3 active, then we will assign that to sig7 break. If it has 4 active, then we will assign that to sig4 break. And finally, if it has all 7 active, then we will assign that to sig8. Although that doesn't actually give us that much information, because no matter what, you know, all the bits are going to be active. Okay. Does it not like that? Oh, sig_8. Yeah, forgot the underscore there. And then default, at least in this pass, will do nothing. Okay, so we know definitely what 4 of the digits represent. So let's start defining how to do some arithmetic on these. So I'm going to say signal so we'll say plus, we will do the union, minus, we will do, you know, set subtraction of their set bits. So we'll just OR those bits together, and that will be plus there. And then for subtraction, you can say signal greater minus cos other. Once again, start with this, and we'll say yeah, and I'm beginning to question whether this would just be easier to go with uint8s, but we'll see. So we'll AND it with all the unset bits so that, anything that's set in other is not set, and we'll return result. So now we can say that the signal for segment A, the upper segment, is equal to the signal for 7 minus the signal for 1. How useful is that to us? We'll see. Looking at this puzzle some more. Don't know how useful that information about A is to us. I mean, we can also say, like, signal for segments B and D is sig4 minus sig1. So I guess I'm looking at all the ones that have to have A, B, and D now, which are 5, 6, 8, and 9. We know that 1 is CF, so 9... So 8 is known, and 9 would be the only one that has A, B, C, D, F. And also G, but is not the same as 8. So I think we have enough to figure out what 9 is now. So... solving this, kind of making up the algorithm as I go, just working out the geometry here. So, Let's write another function called contains. I guess we could make this, you know, an arithmetic operator too, but yeah. So if we do the bitwise AND of the segments from both of them, and that's equal to the segments in the other, then we can say that, you know, it contains everything that's in the other. So if pattern contains sig ABD, so all of A, B, or actually, A, B, C, D, F will equal sig ABD plus sig 1. Sig ABD, AB, C, D, F. And the pattern is not equal to the signal for 8, then it's sig 9. Gonna write the not equal operator here as well. Just got to do that and we're good. Okay. Make sure we found it there. Okay. Now we know what 9 is. And by subtracting 9 from 8, we can know what E is. So, you know, maybe that's useful. Okay. So the only other element that has exactly 6 segments active is 6. So now that we know what 9 is, the only other one with 6 will be 6. So we'll go ahead and make another pass through the signals. Go through all the patterns. And we will say if pattern does not equal sig 9 and pattern and the pattern's number of active segments is equal to 6, then it must be, we'll call that pattern sig 6. Sorry. Signal. I'll remember my class names here. Sig 6 is equal to that pattern. We'll go ahead and use that found variable again too, just as a safety check here. And once again, we can do that same subtraction trick with 8 and find out what C is. So we'll say C is equal to the pattern for 8 minus the pattern for 6. Okay. So we know 6, 7, 8, 9. And 1 and 4 now. So now, oh, you know what, though? That's not strictly correct. I'm sorry. 0 also is 7 segments. So, excuse me, is 6 segments. So, but 6 will be the one with 6 segments that does not contain everything that we know is set from 1, whereas 0 will contain everything that we know is set from 1. So we can use that to distinguish them. So we'll actually get both of them in this loop. And actually, maybe we'll just use like an int to count up found in the in each of these loops that we make over each pass we make. So and we'll do it up at the start here too. So we'll say increase found each time we find something. For our little safety checks. Should be 4 there. Reset to 0. Reset to 0 again. Okay. If that pattern contains 1, then it will be the signal for 0. Otherwise, it will be the signal for 6. In either case, we will increment the count of found. And in this case, we will not break because we want to find both of them. So we'll check found is equal to 2. So we can still get that, you know, C equals 8, and we can actually get D. We can actually specifically get what D is as well, which is going to be 8 minus 0 is going to give us that middle segment. Okay. So we've got 0, 1, 4, 6, 7, 8, 9. Okay. Now let's go down one. Let's look at which numbers contain 5 segments. So that's going to be 2, 3, and 5. Okay, all the remaining ones contain exactly 5 segments. So they're all going to have D set. The only one that will not have C set is 5 of the remaining ones. So let's go ahead. What other patterns do we know here? Okay. I'm also going to do F because, yeah, we can use that to distinguish. Yeah, so F equals 1 minus C. Okay. So of the remaining ones that have 5 segments, we know, let's see here, that both C and F are going to be set for 3. Only C is going to be set for 2, and only F is going to be set for 5. So I think we can find all the remaining digits now. So once again, going through all the patterns, we'll say if the number of active segments is equal to 5, then we're actually concerned with it. So if the pattern contains both C and F, or essentially 1, then it must be 3. Else, if it contains just C, then it must be 2. Otherwise, it better contain F and be 5. In any case, we increment the count of found, and then we just safety check that we found 3 things. Okay, so now we have our complete list, and you know, at this point we can make a little lookup table, I guess. To easily look up digits in the output. So let's go ahead and do that. Show that my making this type hashable was not for naught. So we'll say and then we'll just do this for, you know, all of the digits. Okay, so there we have our lookup table. And then we will go ahead and put together the outputs. So we'll say start with display value equals 0, and then for each output signal in the outputs, we will say an iterator to the value is equal to lookup table dot find that output signal. Make sure that that is actually a valid value in the table. And then we will say display value So if display value held anything from previous digits, we'll multiply that by 10 and then add the value from the lookup table. No, it'd be value it pointing to the second value there. And then we return the display value. Okay. This is a little messy. I'm not sure we needed all the signals that we calculated, but I think this gives us what we need. So now total outputs we can get by summing up the result of solve on each display. We need to add a dependency in our build file for flat hash map from the containers library, which we used for our lookup table. But now let's give it a whirl and see if this works. Okay, immediately there's a problem. Oh, it's not containers plural, it's just container, isn't it? Here we go. Okay, so one of our checks failed on line 155. We expected to find... Okay. We're looking for 6 and 0 here. Put a little debugging statement in here just to see if it finds anything for us. Okay, so it finds 0. It does not find 6. Oh, it's because we still have that break statement in there. That's why. Because when we're looking for 2, we should not be breaking immediately like that. Yep. Just that left over, I think, is probably going to be the whole problem. Okay, 990,964. Let's see if that result is correct. All right, we got it. Let's see where our stats were. Okay, part 2, pretty good, coming in under 2,000. That is our second best result so far. So what I strongly suspect is a lot of people like me were kind of like slowly trying to work through the solution for part 2, figure out, okay, we know 4 of these digits right away. What can we find out next? Okay, now we know that. What can we find out next? And just iteratively getting to a point where they find out all of the digits. Ways that this could maybe be made a little bit more efficient is, like having just a bag of like unknown digits or maybe like pre-sorting digits by the number of active segments so that you don't need to loop over the whole thing. But honestly, like the number of input patterns is fixed and the number of times you have to loop through them is fixed. So like, this is essentially still a constant time algorithm to come up with a solution. Even if it's not the very most efficient, like it's still in the best complexity class that we could expect. So yeah, I think that's pretty good. I like this. I may clean this up a little bit. I don't know, but but I'm pretty happy with what we got, and that it worked the first time for even, well, aside from, our check failure. But hey, that's why we put the checks in. That's why we have those safety checks, is to find those little logic errors. So yeah, thank you very much for watching. Again, if you are watching this live on Twitch, you can find stream replays on my YouTube channel and the code in my GitHub repository. Just check my Twitch channel description. You'll find all the links there. If you're watching the replay on YouTube, you can find links to the Twitch live streams and to my GitHub repository where I upload all the code that we work on right down in the video description. Thank you again for watching, for joining us for this first, actually kind of, like interesting and difficult puzzle, I think, of this year's Advent of Code. And I hope to see you again tomorrow night. Good night, everybody.